Hi guys, welcome to my YouTube channel. Today I'm going to revise D and F block elements for you and tell you just a day or two before your board exams or any of your terminal exams in school, how can you quickly revise this chapter and what are the important questions that can be asked per topic. So without wasting any time, let us go ahead. The first topic here is the introduction. Within this topic, what are transition elements, what are inner transition elements, from which elements each series starts, like 3D from scandium to zinc, 4D from yttrium to cadmium, 5D from lanthanum and hafnium to mercury. So you need to know the first and the last element of each of these series and the lanthanoids and actinoids. These are the questions that can be asked because according to the latest CBSE sample paper, good questions, some applied questions related to NCERT can also be asked. Transition elements fall between S and P. And what is the difference between D block elements and transition elements is what you need to know. Which of the following is not a transition element? The answer is D part, that is lead. It's a group 14 element. Why? Which of the D block elements may not be regarded as transition elements and why? The elements zinc, cadmium, mercury are not regarded as transition elements. They are only called D block elements. Why? Because only those elements are called transition elements which in their common oxidation states or in their normal ground state have incompletely filled d orbitals. Zinc, cadmium, mercury in general have the configuration Ns2, N-1, D10. They have the configuration Ns2, N-1, D10 and their common ion is M2 plus ion, that is Zn2 plus ion. Zinc does not show any partly filled d orbitals. The configuration of Zn2 plus is 4s0 3d10. Since neither in zinc nor in its common ion it shows partly filled d orbitals, hence it is not a transition element, but since the last electron enters into penultimate D, it is a D block element. Same applies to cadmium and mercury as well. Remember, there's a difference between 3D series. 3D series is the first transition series, 4D series is the second transition series, and 5D series is the third transition series. So 5D series starts with lanthanum and ends at mercury. In the D block, the elements which do not generally show the characteristics of transition elements, we've just talked of, these are zinc, cadmium, and mercury. Though copper, silver, gold have completely filled sets of d orbitals, yet they are considered as transition elements. You know, the configuration of copper is 4s1, 3d10, it is Z29. And copper 1 plus also does not have any partly filled d orbitals, but copper 2 plus ion has a 3d9 configuration. Similarly, gold 3 plus has a d8 configuration. Hence, copper, silver, gold are considered to be transition elements. The next question we have, iron, cobalt, nickel are collectively called as, iron, cobalt, and nickel are collectively called as ferrous metals. And copper, silver, gold are collectively called as coinage metals. So this is a question that can be asked from these paragraphs. The general configuration, general electronic configuration of D block elements is, and then electronic configuration of a transition element X in +3 oxidation state is given to you. What is its atomic number? So any question of this kind related to writing down the electronic configuration, like this question is NCERT exercise question. So writing down the electronic configuration or a question of this kind where electronic configuration in a particular oxidation state is given. So how will you go about argon 3d5 and it's a +3 means 3 electrons have been removed. So 3 electrons have been removed means 2 electrons from 4s might have been removed and 1 electron from here might have been removed. So the original configuration might have been 4s to 3d6, which means it's iron, atomic number 26. Write electronic configurations of any of these atomic numbers. General configuration of group 12. Group 12, which is also group 2b according to Mendeleev's classification. So if they ask you, the general configuration is going to be NS2, N-1, D10. So this way, general configuration of any group can be asked. So each of the in-text questions, I'm not repeating here, each of the in-text questions plus the NCERT exercise questions. All these should be definitely done. And then NCERT exemplar questions. So these should be done. And under physical properties, so how are you going to remember these? Most of the metals this side are HCP. And then in between, we have more of BCC. And this side again we have more of CCP, and finally the zinc, cadmium, mercury and manganese, they have one or more typical metallic structures at normal temperatures. So like zinc, cadmium, mercury, these have zinc and cadmium have HCP. Mercury, is a liquid, so there's no solid metallic structure. So in this way, if you can memorize, doing it on the last day, you can leave this part. Properties like hardness and high melting point. Both these properties and high enthalpy of atomization. These three depend on small size of transition elements and more number of valence electrons. And valence electrons are counted by Ns plus N-1 d electrons, right? And if the penultimate d is fully filled, then we count valence electrons as only the Ns electrons. For example, if I'm talking about zinc, then the valence electrons are going to be only 2. Since d is fully filled, so we'll count for zinc valence electrons to be equal to 2. But supposing I want to count it for iron, the valence electrons for iron will be counted as 4s2 3d6 as 8. More are the number of valence electrons and smaller the size. Harder a metal, higher its melting point, higher its enthalpy of atomization. So you can remember these 3 points together. Zinc, cadmium, mercury are soft and have low melting points. This question comes from here, from these lines. Okay, reason? Because they have all paired electrons, no partly filled d, hence less intermetallic bonding. Metallic bonds are weak and low melting and boiling points, and they are soft metals. Out of iron or copper, which has higher melting point, iron has a higher melting point again because of more unpaired electrons, more intermetallic bonding. Among D block elements, the highest melting point is shown by. You can see amongst all D block elements, the highest melting point is shown by tungsten. So the right answer to this is tungsten. In the first transition series, the lowest enthalpy of atomization is for zinc for the same reason. It has no partly filled d orbital. Fully filled configuration, weak intermetallic bonding. 4D and 5D series of transition elements, metals have more frequent metal-metal bonding in their compounds than do the 3D elements because they have larger size. Valence electrons are less tightly held and hence can form metal-metal bonds more frequently. So that's the reason. Coming to atomic and ionic sizes, from 4D to 5D, due to ineffective screening of intervening F electrons, Z effective increases, size becomes less than expected, and therefore similarity of size and hence properties. So all such questions will be based on this point. So we have question forms here. Although zirconium belongs to 4D and hafnium to 5D, they show similar chemical properties. Why? Because they have similar atomic radius. And why do they have similar atomic radius? Due to lanthanoid contraction. So these are the important points related to this one. Similar question can be asked in terms of comparison of atomic sizes of the first series of transition metals with those of second and third series. In the respective columns, the answer is again based on lanthanoid contraction. Then we have density. Here, density is being discussed. Which metal has the highest density out of these? Platinum, osmium, tungsten, and mercury. Osmium has the highest density. Osmium and iridium are the most dense metals. We move on to the next point, that is ionization energy. Now, in general, the ionization energy varies inversely with respect to size. So when size is small, ionization energy is large. So what are the important questions that can be asked? Why is first ionization enthalpy of copper higher than that of sodium? Here, for copper, you know the configuration is 3D10 4s1. For sodium, it is 3s1. So when you remove one electron from sodium, you're going to be left with the noble gas configuration. But after you remove one electron from copper, you will be left with pseudo-noble gas configuration. What is pseudo-noble gas configuration? 3s2, 3p6, 3d10. So since noble gas configuration is more stable, hence, and sodium has larger size, hence the first ionization energy of copper is higher than that of sodium. The next is, why are ionization energies of 5D elements greater than that of 3D elements? This is because 5D elements are smaller in size than 3D due to lanthanoid contraction, and hence the ionization energy varies in this order. Then how would you account for the irregular variation of first and second ionization enthalpy in the first series of transition elements? So in general, you know, size decreases till the middle. Scandium to approximately till manganese size decreases, then it remains nearly same, and then from copper to zinc size increases. So ionization energy also has an irregular variation, the way size varies, and as size becomes large, ionization energy becomes small. Trend is irregular because the removal of electron alters the relative energy of 4s and 3d orbitals. What does this mean? When you place electrons are first put into 4s and then into 3d, because for vacant shells 4s is lesser in energy than 3d. But once the electron is removed, the first electron, that is 4s electron, is removed, there is a reorganization of energies accompanying ionization, and this leads to release of some exchange energy which increases as the number of electrons increase, and hence the ionization energy also varies accordingly. So ionization energy variation is irregular. One very important point that you must know is comparison of ionization energy of copper and zinc. So out of copper and zinc, if we look at size, zinc has a larger size than copper. Why? Because in zinc, there is perfect pairing, and the paired electron repulsions dominate over effective nuclear charge. Okay, so size is large. Since size of zinc is larger than copper, ionization energy variation should also be in this order. Ionization energy is expected to be like this, but actually zinc has a higher ionization energy than copper. The radius of zinc is higher. Ionization energy is also higher. Why? Because of a stable configuration. Due to stable configuration, ionization energy of zinc is greater than copper. And then there's comparison of first ionization enthalpy of chromium and that of zinc. Electronic configuration of zinc is fully filled. Stable configuration 3d10 4s2. So it's difficult to remove an electron from 4s2 in comparison to removing it from 4s1. Hence, the ionization enthalpy of chromium is lower than that of zinc. Compare first series of transition elements with those of second and third. It's a similar question in different set of words as what we've discussed earlier. So regarding oxidation states, number of oxidation states varies, and you can see towards the middle of the table, more number of oxidation states are observed, and towards the extremes, minimum number of oxidation states are observed. This is one point. And second, for all the first two elements, +2, +3 states are more important. So we have M2 plus and M3 plus ions. And these are less important for second and third row element. Why a lesser number of oxidation states are present towards the extremes? So the reason for this is either too few electrons or too many d electrons with fewer orbitals available in which to share electrons with others. So these lines give you the answer why the extremes have less number of oxidation states, but in the middle we have maximum oxidation states. So for the same reason, scandium-2 is virtually unknown. Scandium means 4s2 3d1. This is the configuration of scandium. So it prefers to lose all, hence giving us +3 oxidation state. Scandium-2 is unknown. Similarly, titanium is the next element with 4s2 3d2. It prefers to lose all rather than losing a few. Why? Because there are only few electrons, so it shows an oxidation state by losing all. Titanium-4 is more stable than titanium-2 or titanium-3. And similarly, zinc, the last element, the configuration is 4s2 3d10. It prefers to lose 2 electrons, leaving behind a stable configuration. So the only oxidation state that zinc shows is +2. So these are the questions that are related to this point. Assign reasons for each of the following. Largest number of oxidation states are exhibited by elements in the middle. I've just explained why, because this has maximum number of unpaired electrons. Which element does not show variable oxidation state? Mercury. Zinc, cadmium, and mercury do not show variable oxidation states. They mainly show +2 oxidation state. Maximum oxidation state of osmium is +8. And which of the following state is most common amongst the lanthanoids? +3. Then the next important question that you need to understand from here, the difference between oxidation states of P block and D block. For P block elements, common oxidation states vary by 2 units, such as for group 13, the oxidation states are +1 and +3. For group 14, the oxidation states are +2 and +4. Whereas for D block, the oxidation states generally vary by 1 unit. The oxidation states variability is +1, +2, +3, +4, and so on. And another difference for P block, the lower oxidation state is more stable for heavy elements. For example, for group 13, thallium shows dominatingly +1. For group 14, lead shows dominatingly +2. Although the common oxidation states are +1, +3. Boron shows +3, and till tin, carbon, silicon, germanium, tin, lead, they preferably show +4. So heavier elements, they prefer to show stable lower oxidation states. Whereas for D block, higher oxidation state is more stable for heavier elements. So these are the two differences between the oxidation states that we need to understand, and these are discussed here too. Molybdenum 6 and tungsten 6 are more stable, and the same question can be asked in the form of this. Chromium 6 in the form of dichromate is a strong oxidizing agent, but molybdenum oxide and tungsten oxide are not. Halides of transition metals become more covalent with increasing oxidation states of the metal. The reason, as oxidation state of the metal increases, size of the transition metal ion decreases, and hence, according to Fajan's rule, more percentage of covalent character is observed. Now, trends in the M2 positive to metal standard electrode potentials, that is standard electrode potential of the metal 2+ plus 2 electrons converting to M. So in this, the important point is the highlighted point. Why copper does not react with dilute mineral acids to liberate hydrogen gas, whereas zinc and other electropositive metals can react with dilute HCl to liberate hydrogen gas. What is the reason for this? The reason is high energy to transform copper to copper ion is not balanced by its hydration enthalpy, or in other words, positive E0 value for copper is due to the fact that sum of sublimation enthalpy and ionization enthalpy to convert copper to copper 2 plus ion is so high that the important point is it is not compensated by its hydration enthalpy. Whereas E0 value for zinc is negative, that means zinc has a positive oxidation potential, whereas copper has a negative oxidation potential. These are the reduction potential values. These are the reduction potential values. So the oxidation potential of zinc is positive. Hence, zinc can readily undergo oxidation from 0 to +2 oxidation state, whereas copper cannot. These questions are very important. Why is chromium reducing and manganese oxidizing when both have a D4 configuration? And this relates to the T2G for D3 of chromium. T2G means this is done in coordination chapter when you have D3 as T2G3 half filled T2G3 configuration. Whereas manganese has a normal D5 configuration, which is also a half-filled configuration. So both sides, we have a stable configuration. One side D5 half-filled and another side T2G3, which is also half-filled. So because of which chromium ion is reducing and manganese is oxidizing. The next important type of question, children, I have written two questions here. This form of question is important. What is the logic behind this? You have been given different potentials. All these are reduction potentials. For example, this is the reduction potential of chromium, which reads minus 0.4 volt. And here is the reduction potential of manganese, right? A positive reduction potential of manganese shows that Mn2 plus is more stable oxidation state. That means Mn3 plus will happily undergo reduction to form Mn2 plus, which is going to be a stable oxidation state. This potential here is negative, which means chromium 2 plus is unstable and it is not easy to convert chromium 3 plus to 2 plus. This will not happen easily. Okay, so this means a negative reduction potential means this product ion is less stable. So you're going to compare these three oxidation potentials, these three reduction potentials given here. A highest value of reduction potential shows that the lower oxidation state, that is Mn2 plus, is most stable. Hence, comparing the potentials, we get this order. Mn2 plus is most stable, followed by Fe2 plus, followed by Cr2 plus. And similarly, the basis of the second question is also same. You just have to compare the electrode potentials based on that stability. The answer is written here, so you can just go through. The next important paragraph is here. This is an important paragraph. One point here we are studying is stability of various oxidation states and stability of oxoanions. So the question that is possible is oxoanions of a metal show higher oxidation states. Why? Because high electronegativity and multiple bond formation tendency of oxygen helps to keep a metal in its highest oxidation state. Fluorine and oxygen are the two best oxidizing agents in the periodic table. Hence, they tend to keep the metals in their highest oxidation states. But out of fluorine and oxygen, this is a still better oxidizing agent to keep the transition metals in their highest oxidation states. Its tendency to form multiple bonds. So what happens with its tendency to form multiple bonds? The same oxidation state is satisfied with less number of atoms. Supposing I was to make something like MnF7. MnF7 means I was needed to place 7 fluorines around manganese, which would have led to crowding. But since oxygen has a tendency to form multiple bonds, only 4 oxygens will satisfy the charge, and hence permanganate, a stable oxoanion can be formed. So I summarize from this paragraph, 2 points are important. One, highest oxidation states of transition metals are generally observed in their fluorides or oxides. Oxygen stabilizes the higher oxidation state better because of its high electronegativity, as well as, more important, its tendency towards multiple bond formation. So next important points we have from this paragraph, from here. This is a point which gives us again possible questions. The questions can be out of cuprous chloride and cupric chloride, which is more stable, and why. So CuCl2 is more stable than cuprous chloride. The reason is Cu2 plus has a higher negative enthalpy of hydration than Cu1 plus. If I just elaborate here, Cu2 plus and Cu1 plus, the electronic configuration of Cu1 plus is 4s0 3d10, and here it is 4s0 3d9. So if we look at gaseous state, in gaseous state, this ion, cuprous ion, should be more stable. Cuprous ion should be more stable in gaseous state because it has a stable configuration. But in aqueous solution, due to small size, of Cu2 plus, hydration energy stabilizes it more. Hence, Cu2 plus is more stable in aqueous solutions than Cu1 plus. The next point is, when Cu2 plus ion is treated with Ki, a white precipitate is formed. Explain the reaction. So, iodide ion, being a strong reducing agent, reduces cupric ion to cuprous ion. So, cupric changes to cuprous iodide, liberating iodine. Also, coupled one compounds are unstable in aqueous solution and they tend to disproportionate. And why is it unstable? Because Cu2 plus in solution is more stable due to its more negative enthalpy of hydration, the point we just discussed. This is a very important question for your school exams, always for boards. How would you account for the increasing oxidizing power in these? This is again due to increasing stability of the lower species to which these are reduced. So if we look at the species to which these convert, for VO2 plus, it converts to from +5 to +4 oxidation state in the form of this ion, that is VO2 plus. And V4 vanadium oxidation state, the atomic number is 23, which means 4s2 3d3, and +4 oxidation means 3d1. So 3d1 is the oxidation state to which it changes. Chromium, from dichromate +6, chromium changes to +3. +3 configuration is 3d3, and manganese changes from +7 to +2 with configuration 3d5. So this is the most stable, followed by this. Due to the stability of these configurations, the order of oxidizing power varies in this order. So I hope this is clear. Then another question we have here, which is a stronger reducing agent, chromium ion or ferrous ion? Make the comparison, children. Chromium 2 plus to chromium 3 plus, the potential is going to be plus 0.41. Why? Because the reduction potential given here is negative. So the oxidation potential will become positive. And to check whether a substance is a good reducing agent or not, we have to compare its oxidation potential. A higher positive oxidation potential means more tendency to undergo oxidation itself, hence acting as a strong reducing agent. So similarly, if I write the oxidation potential of ferrous to ferric, it will come out to be minus 0.77 volt. So which means chromium can be easily oxidized. Chromium 2 plus can be easily oxidized to chromium 3 plus. Hence, it will act as a better reducing agent. This is again an important question. This one and this one. This question is what we've just discussed. Similar question we have discussed. Now we move on to magnetic properties. Under magnetic properties, the important questions are most of the times, what are the two kinds of magnetism, diamagnetism, paramagnetism? Para means presence of unpaired electrons and weakly attracted towards external field. Diamagnetism means having all electrons paired and weakly repelled in an external field. You already know these points. And paramagnetism relates to color. The first type of question is give reasons which indicate which one of the following would be colored. So what you have to do is you have to simply find out their write their electronic configurations and see if they are paramagnetic or not. So in case they are paramagnetic, they will be colored, otherwise colorless. For example, if I'm talking about Cu1 plus ion, the configuration of Cu1 plus will be 4s0 3d10. It is diamagnetic, no unpaired electron, which means it is going to be colorless. But if I talk of Cu2 plus configuration is going to be 4s0 3d9. It is paramagnetic, hence it will be colored. So you can see that copper 2 plus salts are generally blue in color, and cuprous salts, copper 1 plus salts, are colorless. Strong permanent magnetism is ferromagnetic. And which are the three ferromagnetic substances? The three ferromagnetic substances are iron, cobalt, and nickel. These are used to make permanent magnets. These are ferromagnetic, right? And then which of the following ion is colorless? Again, you're going to simply check the diamagnetic nature, and you will find the colorless ion, scandium 3 plus. The formula for magnetic moment is mu is equal to root Nn plus 2 Bm. The substance found to have a magnetic moment of 3.9 Bm. How many unpaired electrons does it contain? So either magnetic moment is given to you and you are asked to calculate number of unpaired electrons. So you'll simply apply the formula. You'll get N is equal to 3. Or you are given electronic configuration and you are asked to calculate the magnetic moment. So any of these, this formula is very important. Questions based on this can be asked. So magnetic nature of elements depends on the presence of unpaired electrons. Which out of the following shows highest magnetic moment? So what are you going to check? The one which contains maximum number of unpaired electrons. This is going to have 3 unpaired electrons. So 3d7 would mean this configuration. 5 plus 2, 7. So we have 3 unpaired. So 3d5 is going to have 5 unpaired. This is going to have 2 unpaired. And this is also going to have 2 unpaired. So which out of these shows highest magnetic moment? The one with maximum number of unpaired electrons. So magnetic moment is associated with spin, angular momentum, and orbital angular momentum. Spin only magnetic moment from chromium ion. Again, what you have to do is chromium 3 plus ion. The configuration for chromium is 4s1 3d5. This will be 4s0 3d3. 3 plus. We have removed 1 from 4s and 2 from here. We are left with 3 plus. So root of 3, 3 plus 2, that is root 15. This is going to be the magnetic moment. So the answer is going to be 3.87 Bm. For this question, permanent magnets are generally made of which alloy? Permanent magnets are made from iron, cobalt, nickel, all these. So the answer to this one is D part. Formation of colored ions, either paramagnetism and relating to DD transition. The second type of question and second reason for color is some ions such as KMnO4, potassium dichromate. These have diamagnetic species. Manganese in +7, chromium in +6. These are diamagnetic ions but still intensely colored. Diamagnetic but still intensely colored. So in this case, the color is due to charge transfer spectra. The color is due to charge transfer spectra. So these are the two aspects that you need to keep in mind regarding this topic. What is the reason for color? Electrons from a low energy d orbital excited to higher energy of excitation corresponds to frequency of light absorbed, which you do in detail in coordination chapter. And this frequency lies in the visible region. Color observed is complementary to the color absorbed. The complementary colors are observed through Vibgyor. This is violet, blue, green, yellow, orange, and red. So which means these are pairs of complementary colors. If a substance absorbs green, it appears red. And if it absorbs blue, it appears orange, and so on. Right? So this is the color wheel, which helps us to decide the complementary colors. So these are the points on the basis of which questions can be asked. Scandium is colorless in equation, while titanium is colored. Again, you will write the electronic configuration. Check para and dia. The one which is paramagnetic is colored, the other one is diamagnetic. Give reasons for the following. Transition metals have high enthalpies of atomization. We have already discussed it earlier. Why? Because of small size, more number of valence electrons, and hence stronger intermetallic bonding. Most of the compounds formed by transition metals are colored due to paramagnetic nature and DD transition. Transition metals and most of the compounds show paramagnetic behavior due to partly filled d orbitals. Paramagnetism is due to partly filled d orbitals, and transition metals form complexes due to vacant d orbitals. Please be clear about these two words. Transition metal complexes due to vacant d orbitals, whereas paramagnetic behavior is due to partly filled d orbitals. Catalytic properties. Why do transition metals act as good catalysts? The reason for these metal surfaces provide good surface area for adsorption of the substances. Second is they have variable oxidation states. Formation of interstitial compounds. Why? Because some small atoms like hydrogen, carbon, nitrogen, etc. can get trapped within their crystal lattices. This is the reason why they form interstitial compounds. What is the nature of these interstitial compounds? These are non-stoichiometric, neither typically ionic nor covalent, and these are the properties that can change as a result of formation of interstitial compounds. So the 3-4 points that I've spoken, each one of these is important for a question from this topic. Formation of interstitial compounds makes the transition metal. So this question from here you will pick up makes the transition metal more soft. Is that right? It makes them hard, more ductile, no, more metallic. They have high melting points. They are more hard and brittle. So which point are we supposed to pick up? It will be D part. Chemically inert and they lose their ductility. Now, why do transition metals form alloys? It's because of similarity in sizes. I'll just give you an overview of this in this video. For potassium dichromate, this is more of learning. So for potassium dichromate, first thing that you need to understand is preparation. Preparation of dichromate from chromite ore. This is an ever important when it comes to KMnO4, preparation of KMnO4. And then the difference of solubilities. This point is important. Why don't we directly convert it to potassium dichromate? Why do we need convert it first to sodium dichromate and then to potassium dichromate? Because of the solubility reasons. Then here, this particular part can be asked as what the pH dependence of chromate dichromate equilibrium. That means how do they interconvert on changing pH? What happens in acidic and basic medium? The next important part is knowing the structures. Structures of both dichromate and chromate ion. Then this reaction, this is what happens to dichromate in acidic medium. It changes from dichromate to chromium ion. Both sodium and potassium dichromates are strong oxidizing agents. Sodium salt has a greater solubility in water. This is the point we made use of while preparing as well. And also potassium dichromate is used as a primary standard. Very important. Primary standards are those substances whose standard solution can be prepared by direct weighing because they are obtained in pure form and do not have problems like hygroscopy, etc. And then you need to understand from here, children, mainly since this acts as an oxidizing agent, so you must remember what happens to iodide. Iodide is converted to iodine, H2S to sulfur, stannous to stannic, ferrous to ferric. These points you need to know. For KMNO4, again the preparation, the first important point is its preparation. For both dichromate and KMNO4, preparation is important, and also the names of the ores. Pyrolusite ore, this is pyrolusite ore, and their chromite ore. You must know the formula. These can be asked as 1-mark questions. And then 1-mark questions like give a reaction of disproportionation of K2MnO4, or what is the color of K2MnO4. It's dark green in color. These points should be learned. Potassium permanganate is not a primary standard. It's very difficult to obtain this in pure form. It generally has an impurity. Then the structure of both manganate as well as permanganate ions. Intense color is due to charge transfer spectra. Fine. And then the oxidizing action. First, you need to know these three equations. These three equations in acidic, basic, and alkaline medium, what does it convert to? And then in different medium, what are the products formed from each case? So two types of questions are asked, children. Either they can ask you to write down the balance equation, complete balance equation, or to comment on what happens, like what will be the effect of KMNO4 on iodide ion in acidic medium. So you need to understand in acidic medium, iodide is converting to iodine. But if we look at alkaline medium, you can observe iodide here is converting to iodide. So these kind of variations and the outcomes you must learn. There's nothing that can be taught here. You need to be learning these points. And then coming to KMNO4 titrations. For KMNO4 titrations, we use dilute sulfuric acid. So a question can be asked, why not HCl? So if we use HCl, some KMNO4 is used to oxidize. Hence, if you're talking about titrations, the titer value increases. Why not nitric acid? Because nitric acid itself is an oxidizing agent. So titer value decreases. It's just like it helps KMNO4 to oxidize whichever main substance we are using it for. Okay. And then go through the uses. Coming to lanthanoids. Lanthanoids, the common oxidation state is +3. Then lanthanoid contraction. What is lanthanoid contraction? Causes and consequences. It is the decrease in size with increase in atomic number. Then what are its causes? Causes due to ineffective screening of intervening F, right? And what are its consequences? Similarity in radius. So these are the important things that come under this topic, lanthanoid contraction. Then oxidation states, you have to understand the most common oxidation states are +3 and sometimes +2, +4 can be observed most of the time whenever you get F7 or F14 configurations. So this is the basic reason behind reducing action, oxidizing action of the various oxidation states, a tendency to convert to the more stable half-filled or fully filled configuration. Here also we have an important question. Cerium-4 is used as a good analytical agent. Why? Because of the oxidation states again. So you're going to go through this. I'll make a separate one on details of lanthanoids, actinoids. I'm just giving you a quick overview. Otherwise, this video will become too long. So here, again, we have some important points. The basic characteristics points are similar to D block with most of the times reasons like color, complex formation, all these based on, instead of availability of d orbitals, availability of f orbitals will be the reason when we're talking about lanthanoids. Okay. And then the first ionization enthalpy of lanthanoids are around calcium. This is again a very important point. Basic nature of lanthanoid hydroxides resembles that of alkaline earth metal hydroxides. So we have an important question in this paragraph. In general, Ln stands for all lanthanoids and La stands for lanthanum. And then we have these properties all put in the form of this flowchart. This flowchart explains all the properties, and it's very easy. If you're talking about a reaction with oxygen, lanthanum, you know, is +3. The oxidation state of lanthanum is +3, which means the formula of oxide is going to be Ln2O3, right? So this way you just have to remember all the formulas. These uses, these are important. What is Mish metal? Give its use. So this entire paragraph is important. Uses, Mish metal, its composition, and where is it used? It is used in these making bullets and all this. So this paragraph is again very important when it comes to uses. Actinoids, similar to lanthanoids, read, compare, and finally, an important point will be compare the properties of lanthanoids and actinoids. They are similar. There we have everything related to 4f electrons. Here regarding 5f electrons. Okay. And again, the uses here will be important. And here we have Ziegler-Natta catalyst. You have to remember the composition. Very important. V2O5 catalyzes the oxidation of sulfur dioxide. Catalytic action. Ziegler-Natta, then Brackel process. Catalyzed by which out of these catalysts? And in photograph. These are important points to be gone through, to be read. So I close children here because otherwise this will become too long. And some other time, maybe I make a detailed video on discussing lanthanoids and actinoids. I'm repeating, whenever you're preparing your D block for boards, school exams, terms, units, boards, anytime your sequence should always be learning through the NCERT first, then the NCERT exercise, then the exemplar. Okay, after you've done all this, you still have time, then the conceptuals from any reference book. So that completes your, good preparation of this chapter for your exams. And the entire year round, I would suggest that you give it a repeated learning, because this is one chapter. Inorganic chapters generally do not stay in your memory for long till you give it repeated learning. So thank you. I hope this helps. Please like, share, subscribe, and put in comments what other kind of help you would appreciate. And if this video was good or not, you can share your comments. It would help me to make better content in future. Thank you, and all the best for your exams.